Hello, y'all. Welcome to lesson 99 of my DP chemistry curriculum. Today we're going over reactivity 3.1.8, how pH curves for neutralization reactions involving strong acids and strong bases have characteristic shapes and features. So we'll sketch and interpret the general shape of that pH curve. Before we even go into this, we have to talk about the qualitative techniques for which we obtain or do reactions with acids and bases. So generally, we're looking at very specific qualitative techniques for neutralization reactions. And remember, neutralization reactions is a acid plus base. And we're using qualitative techniques, meaning we are getting numerical data. So we're not using like a litmus test, which just tells us whether something's acidic or basic, but we're getting actual numerical values. But that doesn't just mean the pH, we're also talking about volumes. The main qualitative technique we use for acids and bases is titration. Titration is one of the most common lab techniques that students and scientists do all the time throughout college, throughout their careers, because it is very good for finding exact amounts. This is where we combine a known concentration of something. We call this a standard solution with an unknown concentration of something else, but this will have a known volume. By combining the known with the unknown, we can then produce data which tells us, or we can provide the stoichiometric relationship, which means we can calculate unknown concentration. I'm just using the concentration symbol so that I don't have to keep writing it out. Generally, a titration looks a little like this. You've got your burette, which you are generally using a conical or Erlenmeyer flask. So this is our burette. We have our known solution. This is our standard solution. It is a known concentration, and the burette has measurements so that we can know exactly how much we are putting in, and that funnels into our unknown solution. Now, our standard solution that we pour in is called the titrant. As it's being titrated in, our unknown solution, the one we're analyzing, is called our analyte. So these are just the terms you'll often see in a titration. Furthermore, we're going to add a little bit of indicator. In most acid-base reactions, our indicator is phenolphthalein, which is colorless in an acid but turns pink in an alkali solution. We will slowly add our titrant in, and after a while, let me just go ahead and duplicate that over. After a while, we will notice a color change. Like I said, phenolphthalein turns pink, and so we have a color change. That color change tells us that we are at the end point. We have finished our titration. And so this is a technique we use quite often to qualitatively figure out the amount of hydrogen ions in an acid or hydroxide ions in a base, because we can use stoichiometry and our calculations to figure out, based on the volume of titrant we've used, the amount of moles of reactant in our unknown solution. With that said, let's go ahead and actually just kind of write out some of the key aspects of this. Our burette, that is filled with titrant. That is our going to be our standard solution. We always put our titrant in our standard solution so we can measure out exactly how much we put in. And we put it into our analyte, add to analyte until color change. This color change represents what we call the equivalence point. You can guess kind of from the meaning of the word equivalence point, it's when there's equivalent amounts, but the actual term we use is there are stoichiometrically equivalent amounts, meaning that based on the equations, we have equal numbers of moles of our titrant and analyte within that container or within our Erlenmeyer flask. This is also why our equivalence point is often referred to as the stoichiometric point. Whoops, forgetting how to spell stoichiometric. Stoichiometric point. So we often refer to that. And that is how we can then figure out our titration is done. Using this data, we can create a pH curve. So a pH curve is going to visually represent change in pH during a neutralization reaction. If we are adding acid to base, acid into base, pH starts low, or sorry, starts high, then decreases, which is kind of obvious because our pH is high in the base, and as we add the acid, it will neutralize that, bring the pH down. If we're adding base into acid, it's the exact opposite. pH starts low and then increases. So the thing about a pH curve is what we're really doing is we are creating it by measuring titrant added into solution. And by that, I mean we are controlling it. That's going to be our independent variable. And then we are checking pH with each volume added. And that pH is going to be our dependent variable. So our pH curve is literally just the measure of the amount of added titrant graphed against our pH. Volume titrant added. That will usually be in milliliters or centimeters cubed. So with our pH curve, we'll generally measure against our pH 8, 10, 12, 14. And we have a couple different pH curves that we often see. However, in the SL curriculum, you only need to know two, and we're going to go over both of these. So with this first curve, we start low. Oops, already don't like how I'm drawing it. And we have this gradual increase. Then we reach the sharp increase. I'm going to change that up a little bit. And so this is our first pH curve. It has a couple key points of interest. We start low. This is going to be the pH of acid, of our strong acid only. And that's because only our strong acid exists in solution. Then as we start adding titrant, we get this gradual increase. Oops. Gradual increase because we're neutralizing some of the hydronium ions in solution. Therefore, there is less, and using our pH equation, we can tell that the pH will increase. Then all of a sudden we have a sharp increase. Now the key aspect of the sharp increase is right smack dab in the middle of it, which coincidentally is at a pH of 7. This is our equivalence point. For a strong acid, strong base titration, it will always be an equivalence point of 7. There is only salt and water in the solution. There is no excess acid, there's no excess base. Then as we continue adding base, we get this upper part of the curve, and this is where our base is in excess. And so we have a high pH. And so that's your titration curve. Now, the only other titration curve that you need to know in the SL curriculum is the inverse one. We'll just delete the aspects we don't need. Oops. And for the pH of our strong base, strong acid, it's going to be the exact opposite. We're going to start high, slowly decrease, then a sharp change, then sharp change back. And once again, we have our equivalence point at 7. So a strong acid, strong base graph always starts very high in like the 13 to 14 range, ends low in the 0 to 2 range, and we have this equivalence point at 7. We also have these very sharp curves here as we hit our inflection point on this graph. You'll notice that as well in the strong acid, strong base. And so those are those key features you want to look out for. So this is about it for pH curves. I hope this helps and have a great day.